completed? Yes or no? So when units are completed, yes or no? So today we will be starting with our last unit. Name of this unit is lattices and Boolean algebra. So up till now we have seen in unit 7 groups, in unit 6 monoids and semigroups. From actually unit 6 we started with algebraic system. Okay, in that algebraic system monoids were there, submonoids were there, groups were there, semigroups were there, and in 7th unit then we saw groups. Okay, and now unit 8 is lattices. This is one more type of algebraic system, lattices, and Boolean algebra is again a different part from that. But for this we will see these lattices. Contents of this unit are lattice as posets. Posets again here meaning is partially ordered set. Okay, algebraic system is nothing but a partially ordered set. Yes or no? Because it is containing a set and operation performed on that set. Okay, it is nothing but the algebraic system. Now, how lattice is there? It is acting as a partially ordered set that we are going to see in this subbit. Then definition, examples, and properties of these lattices. Then what are the special lattices? That is also the next content of this unit or chapter, we can say, for that matter. Then again, it starts with this Boolean algebra definition and examples, and then Boolean algebra. Sorry, Boolean function. Okay, these are the contents of this unit. So we will be starting with this. What is a lattice? A lattice is an abstract structure studied in the mathematical subdisciplines of abstract algebra. Okay, again, abstract algebra means the algebra now we are studying, algebraic system in that we are studying. That is nothing but the abstract algebra. What is a lattice? Lattice is an abstract structure studied in the mathematical subdiscipline. Lattice is the abstract structure. It is only said in this sentence. It consists of a partially ordered set in which every pair of elements has a unique supremum. Okay, now what this supremum is? Also called a least upper bound or join. Okay, what it is called? It is called as least upper bound. What a lattice consists of? It is a partially ordered set in which every pair of elements has a unique supremum. It is a partially ordered set, so it will contain the pair, and that pair will contain the unique, this least upper bound, and a unique infimum. Infimum is what? It is greatest lower bound. it is least upper bound and greatest lower bound. Means what? A lattice is a partially ordered set in which every pair of elements consists of least upper bound and greatest lower bound, or it consists of join and meet, join of elements and meet of elements. Okay, it is nothing but the lattice. As an example is given by the power set of a set partially ordered by inclusion, for which the supremum is the union and infimum is the intersection. Okay. Here, what the example given is power set of a set. If I have any set, okay, I can take a power set from that set. Here we will suppose taking. Suppose here we have set A is equal to one and two. Okay, so power set of A. What will be power set of A? Is anybody able to tell me? Yes, power set of this will contain 5. Here, suppose I am taking 0 instead of 5. 5 is nothing but null set. 0, then 1. It will be again in set 1, comma 2 and 1, comma 2. Okay, this is the power set of A. If A is of containing 2 elements, 1 and 2, power set of A is containing 0, 1, 2 and 1, 2. Like this, the power set elements will be there. Now what the case is here? What example we are going to give here is power set of A partially ordered by inclusion, for which the supremum is union. Okay, supremum is union and infimum is intersection. Okay, A and power set of A. If we take example like this, A and power set of A, union of this will be the supremum, that is least upper bound, and intersection of these two will be the greatest lower bound. Tell me what will be the supremum then? See here, A is this one and power set of A is this one. What will be the union of these two? A and power set of A. What will be the union? 5, then 1, then 2, then 1, comma 2. This is the supremum. Means what we have done, we have taken union of these two sets, union of A and union of A with power set of A. It is coming like this. Okay, means what it is supremum. Now what will be infimum? What will be infimum? Infimum means what? Infimum means intersection. What the intersection of these two sets will be? 1, 2 only. 1, 2. Because this is the only common element in these two sets. So 1, 2. This is only the infimum. Getting? A and power set of A. In that supremum, that is least upper bound, that is union, will be the supremum, and that will be like this. And infimum, that is greatest lower bound, will be like this set 1, 2. Okay, and it will contain containing in the lattice. Okay, so for a lattice, one element will be this one, supremum, and one element will be this one, infimum. Okay, it is the lower upper bound, and this is the this is upper minimum. What was the name given? Least upper bound. Yes, sorry. It is least upper bound and it is greatest lower bound. Okay, infimum is greatest lower bound and it is supremum is least upper bound. Okay. I hope you are getting this. Okay, this is the example of lattice that we saw with the help of a whiteboard. Now, another example is given by natural number. Okay, natural number starts from 1 to infinity, partially ordered by divisibility. What the operation given here is divisibility, for which the supremum is the least common multiple and infimum is greatest common divisor. Now you know this LCM and GCD. Yes, you know the concepts that LCM and GCD. Those are the examples of these lattices. Okay, the example another is given with the help of natural numbers. In that, the supremum is least common multiple, that is LCM, and GCD is, that is greatest common divisor, or infimum, is the second element of this partially ordered pair. Okay. Then here examples are given. We can see if L less than or equal to. Okay, this is given the operation symbol, we can say. Okay, this is L less than or equal to, it is the symbol, is a partially ordered set, and S is subset of L is an arbitrary subset, then an element U which belongs to L is said to be upper bound of S if S is less than or equal to U for each S belongs to S. Okay, it is now somewhat confusing. So pay attention here. It is a partially ordered set. Okay, L and less than or equal to. Any operation will be there, then less than or equal to is taken the symbol. Okay, suppose L star, B star, like that we give the operation notation. Here it is given like, star is denoting their operation. Okay, like this here, this less than or equal to is denoting the operation. Okay. Then what is there? S is subset of L. L is the large set. In that, S is a subset of L in an arbitrary subset. Then an element U belongs to L is said to be upper bound of S if S is less than or equal to U. Okay. Here means what is defined? S belongs to L is the arbitrary subset. Then an element U which belongs to L. L is what here? L is our lattice. That U is contained in L. It is said to be upper bound. U ला आपण upper bound म्हणणार आहे. कधी if S is S less than or equal to U. Okay. If S is less than or equal to U. For each S belongs to S. Okay. Each S means the small s belongs to this capital S. Okay. This S is belongs to this capital S, and then again performing the action with U. U is what? Yes. U is what? Here in this, the L is lattice and U is the element in that L. If some connection is there between this S and U, then it is possible to build any relation between S and U or perform any operation on this S and U. For each S belongs to S. This S is smaller than L, okay, because S is subset of L. So if this S is less than or equal to U, then it will be the upper bound. Okay. A set may have many upper bounds or none at all. Okay. What the condition for that is? A set may have many upper bounds or none at all. An upper bound U of S is said to be its least upper bound or join or supremum if U is less than or equal to X for each upper bound X of S. Okay. Now here again same is the case. S belongs to this L. Okay, this S belongs to L. So what it is saying? An upper bound U of S is said to be its least upper bound. Okay. How, in which case it will be called as least upper bound? If U is less than or equal to X. Okay. U is smaller than X. For each bound X of S. Okay. For all of X, this will be treated. Okay. For each X. X are the upper bounds, but what we want is least upper bound. So this is the case. Then what the next is the set need not have a least upper bound, but it can have more than, but it cannot have more than one. Okay. A set need not have any upper bound. Okay, means the supremum. It may not have the supremum, but if it is there, then it will have only one. Okay. No means only unique, that supremum value will be there. Hmm? Now, same is the dually. We can say that L is less than or equal to L. Okay. L here stands for least bound. Okay, sorry, lower bound. Getting L now is here, that is containing in capital L, that is lattice, is said to be a lower bound of S if L is less than or equal to S for each S belongs to S. Then a lower bound L of S is said to be its greatest lower bound or meet or infimum if X is less than or equal to L for each lower bound X of S. Okay, here this L is what we are taking, lower bound. Okay, greatest lower bound. So it again contains in S, that is capital S, that is there. This L is belonging to S for each S again belonging to S. Okay, then what it is there? Then here a lower bound L of S is said to be greatest lower bound or meet or infimum if X is less than or equal to L for each lower bound X of S. Here it is somewhat confusing statements are there. X is again what we can say, it is small than or equal to L. Okay, and each lower bound X of S. Okay, a set may have many lower bounds or none at all, but can have at most one greatest lower bound. Okay, what greatest lower bound will be? It can have one or more, but greatest lower bound will be unique. Means lower bounds may vary, but greatest lower bound will be meaning. Okay, let L be a non-empty set closed under two binary operations called meet and join, denoted by this one. Okay, meet is denoted by this one and join is denoted by this one. Okay, then L is called a lattice if the following axioms hold where A, B, C are elements in L. Okay, then L is called as lattice. How we are going to prove that? Here it is again obeys commutative law. Here it what it will be, A intersection B is equal to B intersection A, and A union B is equal to B union A. What the associative law is? A intersection B intersection C is equal to A intersection B intersection C. Or in for a union operation, what we can do is A union B union C, okay, which is equal to this one, A union B union C. Okay, and the third one is absorption law. A and A or B is equal to A, which is equal to A or A and B is equal to also A. Okay, it is the absorption law. Means what it is saying, this one absorption means Instead of all this term, we can write A only. Same is the case with this term. Instead of all these, we can say only A. So what we can say is it is absorbing other terms. So it is called as A. Okay. Then next example we can see here is subsets of X, Y, Z under set inclusion. The name lattice is suggested by the form of hash diagram depicting it. We have seen this example already, okay? But it is a lattice. How it is a lattice? X, Y, Z are the items. Then phi is there. Then X, Y, Z, three elements are there. Then for the X and Y, the combination will be set XY. Then this one, combination of X and Z will be here, this set, XZ. And what about these two? Y and Z will make the pair Y and Z. Okay, it is the mechanism, we can say, of hash diagram. Here, which sets do we got? XY, XZ, and YZ. Now again combining all these three unions, what it will be there? X, Y, and Z. Because in this one, when combining in union, we do not take repeat symbol. So only what we can take is X, Y, and Z. So this is the hash diagram example also that we have seen. This is the set inclusion. Okay. Then next example given here is lattice of integer divisors of 60 and ordered by divisor. This operation given here is divide, and integer, which integers are there? Which are divided by 60. Okay. Okay. Then how this is there? 1. It goes from 1 to 2, 1 to 6, and 1 to 3. Okay. 2, 3, 6. No, let's see 6 here. It will be 3 then. 2, 3 will be there. Now, which are the items which divide 60? 4 is there, 5 is there, 6 is there. It will be 5, I guess. Then 6 is there, 7 will not be there. 8 also will not be there. 9 also not. 10 will be taken, okay? Because 10 divides 60, okay? Then how many elements are further which are dividing 60? 12 is there, 20 is there, okay? 12 5s are 60, 23s are 60. So this is another example of lattice where what we did here, we took the operation divide and take the number 60. We calculated all the numbers which are dividing this. This is giving us what we can say, lattice. Okay, divide operation is given. Then third is partitions of 1, 2, 3, 4 ordered by refine. Okay, what will be there? You can see. Yes, 1, 2, 3, 4 is given. Okay, or here we can start from here. 1, 2, 3, 4 distinct elements are given. Now, depending on that, what it will do is, depending on that, some type of partitions will be there. How many partitions are there? This is having 4 partitions. Then it will have at least 3 partitions. Okay, so what we can do? 1, 2, 3, and 4. Then 1, 4, 2, and 3. Then what next will be 1, 2, 4, 3. Then 1, 3, 2, 4. Okay. Then 1, 2, 3, 4. And last is the 1, 2, and 3, 4. Okay. How the calculations we can say, or how the division is taken here. Okay, refining operation, how it is performed, that we can see. Now again, what will be done in the next thing? Next step, it is 1, 4, 2, 3. 1, 2, 3, 4. 1, 2, 4, 3. 1, 3, 2, 4. Then 1, 2, 3, 4. Then 1, 3, 4, 2. And lastly 1, 2, slash 3, 4. Okay. All these are the partitions of this one. 1, 2, 3, 4. Okay. Here in this example. This example, what it is, lattice of positive integers. 1, 2, 3, 4. Okay. Here only one axis is given, and the positive integers are 1, 2, giving some gap again 3, then 4. Like this, it gets continued here. Okay. So how it will be given? It will be given like this, a straight line. Okay. 1, 2, 3, 4, and 5 are the examples given there of positive integers. Okay. Now, what the next is lattice of non-negative integer pair ordered component wise. Okay. I cannot see this example. Non-negative integer pair, again it will contain our pairs like 1, 1, 2, 2, 3, 3, like that. Now we can see here. It is considering the points only. What the point it will be? Here in the last example, we are having only one line. Here in this example, we have 2 axes, suppose. So here we will get the point. Okay. So 0, 0 is there. It is here. It is 0, 0 is there. That is included. Then whichever the points are there, these are not visible actually. I cannot see actually this example. But here it is the point 0, 0, and this is the 1, 1. All the points are included here, component wise, whatever the components are here. So this point, what we can call it as, suppose this is the x-axis and this is the y-axis. Then this point will be, x will be 0 and y will be here. Sorry, y will be 0 and x will be 1. So this point will be 1, 0. This point will be 2, 0. Same here, 0, 1. 0 is the x-axis value. So it will be 0, 1. This will be 0, 2. Axis value is 0 and y axis value is 1 and 2 like that. Okay. So like this, all this is the component wise lattice. Okay. All the points are included here. So what this lattice will be called as lattice of non-negative integer pair. Okay. So these are the 5 examples of this lattice. Okay. So next comes is the duality of lattice. What it will be? The dual of any statement in a lattice L, and here we can say it's like intersection and union is defined to be statement that is obtained by interchanging uh, these two, union with intersection and intersection with union. As it we know in the duality what we do. Okay. The example given here is A intersection B union A is equal to A union A. Okay. Dual of this what it is? A union B intersection A is equal to A intersection A. Okay. This is the duality of this what we can say here. Lattice. Okay. Then what the bounded lattice is? Lattice L is called bounded lattice if it has greatest element 1 and least element is 0. Now, one thing we know, okay, lattices are the partially ordered sets containing the elements with one of which is upper, lowest upper bound, and one is greatest lower bound. Okay, so if the greatest element in that lattice is 1 and least element is 0, then that lattice will be known as bounded lattice. What example given here is the power set P of S of the set S under the operation of intersection and union is bounded lattice since this phi is the least element of P of S and the set S is the greatest element of P of S. Okay. This one, whatever the phi is the intersection, so it will be the lower least element, and greatest element will be the power set of S itself. So it will be the greatest element. So what we can say that between phi and power set of S, all the values are containing. So it will be the bounded lattice. Again here, the set of positive integers I plus under the usual order of less than or equal to is not a bounded lattice since it has a least element 1, but the greatest element does not exist. Okay. One example is given here of power set, but here this is not the example of bounded lattice that is given. The set of positive integer I plus under the usual order of less than or equal to is not a bounded lattice. Okay, it's not a bounded lattice since it has a least element 1. You know, the set of positive integers, it is having the element 1, but it is not having any greatest element. because set of positive integers, it starts from 1 but ends at infinity. Okay, we do not know what the exact end of that set is. So that is not a bounded lattice. What are the properties of bounded lattices? You can see here. If L is bounded lattice, then for any element A belongs to L, we have the following identities. What the identities are there? A union 1 is equal to 1. A intersection 1 is equal to A union 0 is equal to A, and A intersection 0 is equal to 0. Okay, these are the identities which are the bounded lattice. Okay, now what the theorem given here is? Yes, theorem given is prove that every finite lattice L is equal to A1, A2, A3, An is bounded. Okay, what we have to prove is that for every finite lattice L is equal to A1, A2, A3, N is bounded. What the proof of that will be? We have given the finite lattice L is equal to A1, A2, A3 up to N. Thus, the greatest element of the lattice L is A1 union A2 union A3 union N. Okay. Also, the least element of the lattice L will be A1 intersection A2 intersection A3 intersection intersection AN. Since the greatest and least element exist for every finite lattice, means L is bounded. Okay. So why the L is bounded? Yes, the greatest and least element exist for every finite lattice. Greatest element, how it will be given? Union of all the elements. Okay. And how the least element will be given? Intersection of all the elements. By this method, we can take up all the greatest and least elements for the finite lattice. So what we can say that this L is bounded. Okay. Then next comes the sublattices. Okay. What the sublattices are here? We can see. Consider a non-empty subset L1 of a lattice L. Okay. What? Non-empty subset L1 of lattice L means L1 is the subset of L. Then L1 is called the sublattice of L. If L1 itself is a lattice, that is the operation of L, that is A union B. If it belongs to L1 and A intersection B, it also belongs to L1. Whenever A belongs to L1 and B belongs to L1. Okay. Sublattice means what? L1 is a sublattice of L, but same operations are performed with sublattice, then and then it will be the sublattice. Means here lattice L, it is A union B is belonging in L1 and A intersection B, that is also belonging to L1. So we for getting it correct, we have this one. A, for that purpose, A must be there belongs to L1 and B also must be belongs to L1. If these two elements are there, it belongs to L1, then this operation also belongs to L1. Okay, and L1 is what? It is subset of lattice L or sublattice of lattice L. Consider the lattice of all positive integers I plus under the operation of divisibility. The lattice Bn of all divisors of n greater than or equal to 1 is a sublattice of I plus. Okay. How the sublattice is proved here? The lattice Bn of all divisors of n greater than 1, because here we are taking all the positive integers. So n must be greater than 1 is sublattice of I plus. Okay. If what are the elements of in that I plus lattice will be there. Divisors of all the numbers will be there in the I plus. Okay. So what we can call it as the lattice Bn of all divisors of n greater than or equal to 1. Sublattice of I plus. Determine all sublattices of D30 that contain at least 4 elements. Okay. Now D30 means what? Division 30. Such numbers which are dividing the number 30. Each number from there, 1, it divides 30, 2, it divides 33, it divides 30, 5, it also divides 30, 6, it divides 30, then 10 also divides 30, 15 also divides 30, and 30 also divides 30. So all these sets, it will be the sublattice of this lattice, which is a positive integer. All these elements are belonging here. Then in I plus. Okay, I plus is what it is set up all positive. Okay. Now, how the solution given here is we can see of D30. What we have to do is that contain at least 4 elements. Okay, then we can take, because here we know 1 is the lower bound and 30 is the upper bound. Then in between we can take anything, but 1 and 30 are common here. 1 is the least bound, 30 is the upper bound. Here also 1, 30, 1, 30, 1, 30, 1, 30, 1, 30. Now the elements between these two elements are continuously changing. 1, 2, 6, 30, 1, 5, 15, 30, 1, 5, 10, 30, 1, 6, 10, 30, 1, 2, 3, 30, 1, 2, 1, 3, 6, 30, and 1, 3, 5, 15, 30. Okay. These are the examples of sublattices. What is the time? Tomorrow we will be finishing our this unit, and we will be finishing our syllabus also. Okay. I hope all of you have got examples given with the help of diagrams for lattice. Okay. Today we will stop here. Tomorrow at 5 p.m. again we will take 1 hour session and we will finish our syllabus. Okay.
Okay, ma'am.
Okay. Just put your attendance in chat box. 8 participants. Put your roll number in chat. All of you have put the attendance. Only 8 students have put the attendance. It will be your loss. Okay. Um, I'll finish the meeting. Tomorrow at 5 to 6, we will again take 1 hour session and then we will be finishing also.